In one of China's most mountainous regions, engineers faced a seemingly insurmountable obstacle. An entire mountain blocked the path of a highway and one of the most extreme bridges on the planet. The solution wasn't to go around it or drill through it, it was to split it in two. Guizhou is not an easy province for engineering. Its landscape is dominated by karst topography, a type of terrain formed over millions of years by the action of water on soluble rocks, especially limestone. From afar, these mountains may appear solid and immutable. From within, they are often quite different. Cavities, fissures, underground channels, hidden caves, and eroded layers that make every project a constant negotiation with geology. For centuries, this same geography shaped the lives of its inhabitants. Roads adapted to the slopes. Villages were separated by canyons and rivers, instead of facilitating movement, acted as barriers. A seemingly simple route could require dangerous descents, exhausting ascents, and long detours. The transport of goods, medicine, tools, or basic materials depended on narrow paths vulnerable to the elements. The Huajiang Bridge project was conceived within this framework. The goal was to cross a gigantic canyon carved by the Beipan River, a chasm so deep it earned nicknames related to a crack in the earth. The bridge was intended to drastically shorten a journey that previously required long mountain roads. Instead of descending endless curves and climbing back up the opposite slope, vehicles would cross the void in a matter of minutes. It wasn't enough to design a long bridge. It had to be built in an area where heavy machinery could barely reach, where the wind howled fiercely, where fog reduced visibility, where the ground wasn't always as stable as it seemed, and where every meter of rock had to be studied before any load could be placed on it. The first difficulty was logistical. To build a bridge almost 3 kilometers long in such a location, it was necessary to transport steel, cement, machinery, cables, cranes, generators, controlled explosives, sensors, and specialized personnel. But many existing roads weren't equipped to handle heavy trucks. The project required temporary roads, makeshift platforms, access roads excavated into hillsides, and transport solutions adapted to terrain that allowed no margin for error. Adding to this complexity was the climate. In a deep canyon, the wind doesn't behave like it does on a plain. The currents accelerate as they pass between rock walls, change direction rapidly, and can generate turbulence that is dangerous for cranes, suspended cables, and elevated platforms. The humidity also contributes to the fog. The rain is affecting the stability of slopes and roads. The work couldn't proceed solely according to the schedule, but rather according to safety protocols. The first logical idea was to use the existing rock as support. In mountain construction, rock formations can be allies if they are stable, compact, and strong. Sound rock allows for anchoring, tunnel excavation, foundation support, and load absorption. But in Guizhou, appearances could be deceiving. The surface displayed imposing walls, but the interior was marked by karst. Karst forms when water, slightly acidic due to dissolved carbon dioxide, penetrates limestone and slowly dissolves it. The process takes thousands or millions of years. The result is a subterranean world of hollows, conduits, caves, underground rivers, and weakened areas. From the outside, a mountain can appear as a solid block. When drilling into it, the drill bit might first encounter solid rock, then a cavity, then a fractured layer, and further down, another compact zone. For a suspended structure, this uncertainty is critical. A bridge anchorage cannot rely on rock that cracks like a crust. It must penetrate material capable of withstanding enormous tensile forces for decades. If cables transmit force to a weakened area, the result can be deformation, cracking, displacement, or progressive failure. In a long-span structure, even a small movement at the anchorage can translate into dangerous stresses throughout the entire system. Geological surveys revealed that some areas did not offer the necessary stability. Drills encountered voids at varying depths. This meant the mountain could not be treated as a uniform block. It was necessary to precisely identify the location of the bedrock, where the weathered layers began, which areas could bear loads, and which should be avoided. A second alternative would have been to change the route. On the surface, moving a highway a few kilometers seems simpler than cutting through a mountain. In practice, a high-speed route cannot be freely drawn across extreme terrain. It must respect maximum gradients, curve radii, stability zones, connections with other roads, and points where tunnels, bridges, or viaducts can be built. Diverting a road too much can multiply its length, increase costs, introduce new risks, and simply shift the problem to another mountain. Drones, topographic surveys, and field studies showed that the surrounding area did not offer an easy solution. Some slopes were too steep. Others were affected by landslides. Still, others required longer tunnels through complex rock formations. The entire terrain seemed designed to block every exit. Another option was to build piers from the canyon floor. This solution is used in many viaducts, raising supports from below and placing the deck on top. But Huajiang Canyon was not a tranquil valley. The Beipan River flows through areas of steep slopes, and during the rainy season, the flow can change abruptly. A pier at the canyon floor would have been exposed to flooding, erosion, impacts from debris carried by the water, and rockfalls from the canyon walls. Furthermore, the greater the height of a pier, the more complex its stability becomes. A structure hundreds of meters tall, subjected to wind, seismic activity, and basal erosion, requires an extraordinary foundation. In an active canyon, where the slopes can send rocks and sediment tumbling down, this option could introduce more risks than solutions. There was also the possibility of excavating a network of tunnels to avoid the main bridge. China has extensive experience with mountain tunnels, but that doesn't mean any tunnel is suitable. A long tunnel in karst terrain can encounter groundwater, cavities, gases, collapsible zones, and sudden changes in resistance. It requires ventilation, drainage, lining, safety systems, evacuation, and constant maintenance. In some cases, it's feasible. In others, the cost and time frame make the alternative inefficient. The calculations pointed to an uncomfortable conclusion. The bridge remained the best solution, but only if the relationship between the structure and the mountain blocking its route could be resolved. This is where the critical point emerged. It wasn't simply a matter of opening a road. The goal was to ensure the geometry of the suspended system functioned correctly. A suspension bridge requires its main cables to follow precise paths. These cables receive the weight of the deck via vertical hangers and transmit the load to the towers and anchorages. If the cables don't reach the anchorage at the correct angle, the forces will be unevenly distributed. If the anchorage is too high, too low, or offset laterally, the bridge can suffer from twisting, unbalanced stress, or unwanted deformation. Cutting through the mountain demanded precision, sequencing, and constant monitoring. The goal was to create an artificial gorge with the most stable walls possible. This gorge would allow the road to pass through and facilitate the integration of the anchoring systems. But the mountain couldn't lose its structural integrity. The challenge was to remove a portion of the rock without weakening the whole. The first step was a detailed survey of the massif. The surveying and geology teams needed to understand its external shape, the slope of the layers, visible cracks, runoff areas, risk points, and the presence of cavities. In modern construction, this information isn't obtained solely from old maps. Laser scanners, drones, drilling, sensors, digital terrain models, and structural analyses are used. Each piece of data feeds into a more comprehensive simulation. Next, the cutting line is defined. This line cannot be arbitrary. It must respect the road alignment, the direction of stresses, the stability of the slopes, water drainage, and the space required for machinery and safety equipment. An excessively steep wall might save on excavation, but it increases the risk of rockfalls. A steeper wall can be more stable, but it requires removing more material and disturbing a larger area. The solution depends on balancing stability, cost, time, and structural function. Excavation is carried out in stages. First, boreholes are drilled in carefully calculated patterns. Not all holes serve the same purpose. Some mark the outline of the future cut. Others fragment the core material. Still others allow control over the direction in which the rock will break. This technique is known as controlled blasting or contour blasting. Its objective is to break rock where necessary and protect it where it must remain intact. Instead of a massive detonation, metered charges and timed sequences are used. Energy is released gradually. This reduces vibration, limits damage to the remaining rock, and prevents the mountain from behaving like an uncontrolled, battered object. In some areas, mechanical methods, hydraulic hammers, saws, drills, or expansive agents may be used depending on the rock type and the sensitivity of the surrounding environment. After each stage, heavy machinery comes in. Excavators, loaders, and trucks remove the loose material. Then the walls are inspected. Specialists look for open cracks, unstable blocks, damp areas, discoloration, or any sign of weakness. On high slopes, inspection work may require vertical access equipment, ropes, platforms, and specialized operators. A freshly cut face is never left to its own devices. It must be stabilized. Rock anchors, bolts, wire mesh, shotcrete, drainage ditches, dynamic barriers, and motion sensors are used for this purpose. Bolts pierce fractured blocks and anchor them to more stable layers. Mesh retains minor rockfalls. Shotcrete protects erodible surfaces. Drainage prevents water from accumulating in cracks and increasing internal pressure. Water is one of the most silent enemies of these structures. In a karst mountain, it can appear through unexpected seepage. If water penetrates cracks and then changes pressure, it can weaken the rock. If it carries fine particles, it can erode internal areas. If it flows behind a slope, it can reduce its stability. Therefore, the cut is not just an extraction operation. It is also a hydraulic control operation. The structural safety of the project depended on knowing if the mountain was moving. For this purpose, monitoring instruments are installed. Inclinometers, extensometers, surveying stations, vibration sensors, and continuous reading systems allow for the detection of minute displacements. In a typical construction project, a few millimeters might seem insignificant. On a slope hundreds of meters high, those millimeters can be an early warning of a major problem. The final image of the cut might suggest brutal force. But the technical reality is more delicate. The mountain was opened with a logic similar to that of a surgeon removing tissue without damaging vital organs. Every meter excavated changed the distribution of internal stresses. Each block removed required checking that the rest remained stable. Every rain, every vibration, and every temperature change could alter the rock's behavior. The most important reason for splitting the mountain wasn't on the surface, but in the direction of the forces. A suspension bridge appears to be held up by two towers and a set of elegant cables. But that image simplifies a much more demanding reality. The deck pushes downward. The hangers transmit that weight to the main cables. The cables convert part of that load into horizontal tension and carry it to the anchorages. There, the ground must resist a gigantic force trying to pull it toward the center of the bridge. In bridges of this scale, the anchorages are as important as the towers. They can consist of enormous concrete blocks buried or embedded in the rock. Their function is to prevent the cables from shifting. To achieve this, they take advantage of their own weight, friction, the geometry, and the resistance of the rock mass. If the anchorage fails, the bridge loses its fundamental balance. The mountain that blocked the route presented a contradiction. On the one hand, it contained sufficient mass to function as a support. On the other hand, its external shape didn't allow for the correct routing of the cables or the placement of the anchorage blocks in the right location. It was like having a huge, strong piece, but one that didn't fit properly into the mechanism. By creating an artificial crack, the engineers were able to modify that geometry. The cut allowed for a more direct path for the road and the structural elements. It also facilitated access to internal zones of more competent rock, less altered by surface weathering. In many mountains, the outer layers are fractured by cycles of moisture, temperature, roots, erosion, and ancient movements. Deeper down, more compact material can be found. The difference between surface anchoring and deep anchoring is essential. A surface slope may appear hard, but if it is heavily fractured, the stress on the cables can dislodge blocks or open existing fissures. In contrast, deep anchoring can transmit the load to a larger volume of sound rock. It doesn't depend on an external crust, but rather on the internal mass of the rock mass. The artificial crack also helped control the continuity of the alignment. A high-speed highway needs reasonable gradients and wide curves. Trucks cannot handle abrupt changes in slope after exiting a suspension bridge. If the road climbs too high, it becomes inefficient. If it drops too low, the risk increases. If it turns sharply, it reduces speed and safety. The mountain was at the point where the road had to maintain a clean transition. In less extreme terrain, a smaller cut, a short tunnel, or a curve would have been designed. At Huajiang, the scale of the canyon and the position of the bridge amplified every decision. A small change in the alignment could displace an entire approach. A displacement of the approach could alter the anchor point. A change in the anchoring could alter the cable tension. A change in tension could affect the deck's behavior in wind conditions. The wind added another layer of complexity. Long bridges spanning deep canyons must be designed to avoid dangerous oscillations. Engineering history recounts instances where wind caused destructive vibrations in bridges poorly adapted to aerodynamic phenomena. A modern bridge deck is designed to allow airflow, reduce turbulence, and prevent resonances. In Huajiang, the mountain cut could also influence how the approach integrated with the canyon currents. Mountains don't just block wind, they also channel it. A convex wall can generate eddies, local accelerations, or areas of turbulence. An artificial opening modifies the airflow. While the primary aerodynamic design relies on the deck and steel structure, the immediate environment also matters. The transition between road, mountain cut, and bridge must avoid abrupt changes that increase exposure to crosswinds or create areas of irregular pressure. Added to this is the seismic risk. In a mountainous region, earthquakes affect more than just buildings. They can trigger landslides, deform slopes, open cracks, and alter the stability of hillsides. A shallow anchor in weathered rock would be more vulnerable if an earthquake were to shake the rock mass. A deep anchor, embedded in more competent rock and designed with safety margins, offers greater resistance. When the mountain was finally opened up, the project was still far from complete. The cut had created the necessary space, but the main task remained, erecting a structure suspended over one of the deepest canyons in the world. The challenge was no longer just traversing rock. Now, steel had to be stretched across the void. A bridge like the Huajiang isn't built from the bottom up, like a conventional elevated highway. The canyon's depth makes relying on intermediate supports impractical. The solution is to suspend the deck from main cables, capable of spanning an enormous distance between towers. This choice allows crossing the abyss without filling the canyon with pillars, but it concentrates the challenge on a few critical elements: the towers, the cables, the anchorages, and the steel deck. The towers function as massive vertical supports. They raise the cables to the necessary height so that they form a strong curve. This curve isn't merely decorative. It's the natural shape a cable takes under load. The geometry of this curve distributes forces, absorbs weight, and transmits tension to the ends. Therefore, every centimeter of the system must be precisely calculated. In a mountain construction project, erecting a tower is already an extreme undertaking. The foundations must rest on stable rock. Cranes must operate on confined platforms. The wind dictates movement. Fog can halt maneuvers. Every piece of steel or concrete must reach an area where roads previously barely existed. The terrain necessitates building the infrastructure that will allow the construction of the final structure. The installation of the cables is one of the most delicate phases. Before the main cables are laid, lighter guide cables are strung. These initial wires cross the canyon and allow for the installation of temporary transport systems. Then, steel wires are bundled together to form massive cables, designed to withstand thousands of tons of tension. The process requires constant monitoring because a difference in length, temperature, or tension can disrupt the balance. Temperature matters more than it seems. Steel expands with heat and contracts with cold. On a long bridge, this variation can translate into centimeters or even more. During assembly, engineers must adjust the position of cables and segments, taking into account the ambient temperature, the time of day, the wind, and the temporary load on the equipment. The bridge does not behave like a rigid object. It moves, breathes, and changes as it is built. Next comes the deck, the platform on which vehicles will travel. On long-span bridges, it is usually formed with metal segments manufactured in a workshop and assembled one by one. Each segment is lifted, transported to its position, and secured to the previous ones. The structure grows from the ends or from specific points, advancing over the void like a suspended steel line. Precision is essential. If even a segment is slightly misaligned, the error can accumulate. If the wind moves the piece during lifting, the maneuver becomes dangerous. If conditions change suddenly, work must stop. In a deep canyon, a piece weighing tens of tons, suspended by cranes or cables, allows no room for improvisation. The deck must also withstand the wind. That's why simply making it strong isn't enough. It must have an aerodynamic shape. The force of the wind doesn't just act by pushing sideways. It can generate vertical vibrations, twists, and oscillations. A proper design allows air to pass through or around the structure without producing dangerous movements. In some cases, deflectors, openings, torsional rigidity, and monitoring systems are added to study its actual behavior. The Huajiang Bridge was built in an environment where height amplifies the perception of risk. Beneath the deck, there isn't a drop of just a few meters, but a void that exceeds the scale of many skyscrapers. The crews worked with harnesses, platforms, strict protocols, and specialized equipment. But even with all the available technology, building such a bridge still depends on extreme human discipline. The cut mountain also played a role in this phase. By opening up the corridor, the connection between the bridge and the highway was facilitated. Access was no longer a forced line along an awkward slope. It became a more direct transition between the suspended deck and the solid ground. This continuity was essential to prevent the structure from ending up as a monumental bridge connected to a problematic road. Many mountains are not as solid as they appear. Our imagination often conjures up a mountain as a compact mass, a stone fortress altered only by earthquakes or visible erosion. But in karst regions, the interior can resemble a labyrinth. Karst is born from a slow reaction between water and rock. Rain absorbs carbon dioxide from the atmosphere and the soil, forming a slightly acidic solution. As this water seeps through cracks in the limestone, it dissolves small amounts of minerals. At first, the process is almost imperceptible. Over time, the cracks widen. Then they become conduits. Later, they can form caves, sinkholes, dolines, and underground rivers. The result is a terrain of dual nature. On the surface, there are mountains, peaks, and walls. Beneath the surface, there are hollows, channels, and voids. For construction, this duality can be dangerous. A pile, a tunnel, or an anchor can encounter an unexpected cavity precisely where support was expected. A road can sink if the underlying ground collapses. A hillside can become unstable if water alters internal pressures. Guizhou has one of the most impressive karst landscapes in the world. This same characteristic attracts tourism for its scenery, caves, and canyons, but it complicates every infrastructure project. There, engineers aren't working against a simple mountain. They're working against a mountain that may conceal another mountain beneath the surface, riddled with voids and weaknesses. This condition fuels stories, superstitions, and strange theories. In many cultures, mountains with deep caves have been associated with spirits, monsters, entrances to the underworld, or hidden civilizations. The human mind tends to transform the unknown into mystery. When a drill suddenly falls into a void, when a river disappears underground, or when a hillside collapses without warning, the landscape seems to behave as if it possesses a will of its own. The real explanation is geological, not supernatural. But that doesn't make it any less unsettling. A karst mountain is a living structure in the physical sense. Water continues to circulate. Rock continues to dissolve. Cracks continue to evolve. Heavy rains can alter the behavior of an underground system. A blocked conduit can increase pressure. A void can collapse. A slope can fail due to causes that began long before any construction work arrived on the site. That's why modern engineering uses increasingly sophisticated tools to peer into the rock. Drilling boreholes bore into the ground. Geophysics detects contrasts beneath the surface. Radar Electrical resistivity, tomography, and other methods allow us to infer hollow or saturated zones. Digital models integrate scattered data to reduce uncertainty. Even so, the subsurface is never fully revealed. In the case of the bridge and the cut mountain, this uncertainty forced the abandonment of simple solutions. The project could not rely solely on the rock's appearance. It had to find resistant areas, avoid cavities, stabilize slopes, and design deep anchors. The mountain was cut not because it was weak overall, but because its shape and internal structure did not allow it to be used as it was. This detail changes the interpretation of the project. It wasn't a battle between humanity and nature, but rather an extreme adaptation to a complex environment. The mountain wasn't a mythical enemy. It was a geological system with its own rules. Engineering had to learn those rules, measure them, and then intervene with sufficient precision to avoid disaster. The mystery, then, isn't in a hidden force protecting the mountain. It lies in the contradiction of a rock that seems eternal and, at the same time, can be riddled with holes. It lies in a landscape that appears static and yet is slowly transformed by the invisible action of water. It lies in the human capacity to read those signs and translate them into a functional structure. The ultimate meaning of the project lies in its territorial transformation. A highway and a bridge of this scale change the way a region relates to itself and to the rest of the country. Before a direct connection, travel in mountainous areas depended on slow roads. Travel time wasn't measured only in kilometers, but also in gradients, curves, weather, and risk. A short journey could consume an entire morning. A truck can use more fuel going up and down mountains than actually moving forward. An ambulance can take too long. A farmer can lose competitiveness because their product arrives late or at a high price to market. When infrastructure radically reduces travel time, the change ripples outwards. Logistics costs decrease. Products circulate more easily. Workers gain access to more opportunities. Services arrive with less delay. Companies can consider areas previously overlooked. Tourism becomes viable for visitors who would not have accepted long and difficult journeys. In Guizhou, the large bridges also have strategic value. The province has gone from being known for its mountainous isolation to becoming a showcase of high-altitude engineering. Its canyons, once seen as obstacles, have been transformed into settings for world records, scenic routes, and new economic activities. The Huajiang Bridge is part of this transformation. The project also incorporates experiential tourism. Such a high bridge doesn't just transport vehicles. It attracts visitors who want to observe the void from glass platforms, panoramic elevators, or observation decks. Vertigo becomes a tourist attraction. The same abyss that once hampered daily life now generates economic activity. This transformation has an ambivalent dimension. On the one hand, it improves connectivity and can revitalize isolated communities. On the other, it introduces tourist pressure, changes in the landscape, maintenance costs, and debates about environmental impact. No major infrastructure project is neutral. It always reorganizes the territory. It always benefits some activities, displaces others, and forces the management of consequences. The cutting of the mountains symbolizes this tension. It is an image of technical progress, but also of profound intervention in nature. The question is not only whether it could be done. The more complex question is when it makes sense to do it. In this case, the answer was based on the need to connect a difficult region, the technical feasibility of the bridge, and the impossibility of resolving the route through more conventional options. Contemporary engineering operates within this balance. Humanity needs roads, energy, water, transportation, and communication. But every solution must coexist with geological, environmental, and social limits. Cutting a mountain may seem excessive if viewed in isolation. Within the complete system, it was a response to a connectivity problem in a remote territory. The split mountain also became a message. It demonstrates the extent to which China is willing to modify complex landscapes to integrate regions and sustain its infrastructure network. In just a few decades, the country has built a vast number of highways, railways, bridges, and tunnels. This rapid pace has resulted in works admired worldwide, but it has also sparked debates about costs, debt, territorial impact, and long-term maintenance. In the case of Huajiang, the public image tends to focus on the spectacular, the towering bridge, the canyon, the open mountain. But for the nearby communities, the most significant change is simpler. A journey that previously depended on difficult roads becomes direct. A remote area is brought closer to the rest of the country. The mental map of the region changes. The mountains no longer disappear. They are still there, dominating the landscape. But they no longer impose the same degree of isolation. The road does not erase the geography. It traverses it, cuts through it, transcends it, and reinterprets it. That is the true power of the project. It is not about denying the mountain, but about changing the human relationship with it.